Alrighty. Morning, everybody. Welcome back to Calc 3. Plan for today is we're going to finish Standard 7 by talking a little bit more about how to evaluate limits of multivariable functions, and then talk a little bit about continuity. Upcoming homework will be the Standard 7 quiz on Wednesday. And as always, there are some practice problems posted on Blackboard that I encourage you to look at if you would like some extra practice looking at these sorts of limits and continuity problems. Standard office hours for the next couple days. So, quizzes. I'm a little bit behind on grading, so I don't have the Standard 6 quizzes graded yet, unfortunately, but I'm hoping to have those back to you on Wednesday. Probably going to try and grade those tomorrow morning if I have to guess. What's I going to say? Yeah, any questions or comments before we get started for today? Did you know that my old car is a lot like e to the x? You can try deriving it all you want, but you're not going to get anywhere. Okay, so last time we kind of talked about what it means to find the limit of a multivariable function, focusing mainly on functions going from R2 to R. And we said that if you want to show that the limit as xy approaches some ab of our function does not exist, what you have to do is to just find two separate directions approaching your point, ab, which in this case would be the origin, along which the limit is going to go to two different values. So in other words, last time we were looking at a limit as xy approaches the origin of x squared over x squared plus y squared. And our approach to show that this limit does not exist was to take a limit along, say, two different paths going to the origin. So for instance, if we were to go along x equals 0, this is just something we did last time, so you don't necessarily need to write this down again. If we go along the path x equals 0, meaning we're approaching the origin vertically from above or below the x-axis, what we're going to end up with is a limit as y approaches 0 of just 0 squared over 0 squared plus y squared, which is just going to come out to 0. Whereas on the other hand, if we were to take a limit along a different direction, say along the line y equals x, which is another path that's going to approach the origin, what we would get is a limit as xy approaches 0, 0 along y equals x of this expression, which would give us a limit as, say, x goes to 0 of x squared over x squared plus x squared, where we've just taken our y's and replaced them with x's. Because along the line y equals x, the y's and x's should be equal. And if we take a limit along this direction, we would get a limit as x goes to 0 of x squared over 2x squared, which would come out to a half. And then what we said last time is since this limit isn't the same along these two directions, along x equals 0, it comes out to 0. Along the line y equals x, it came out to a half. That told us the overall limit without specifying a direction did not exist. And so what I want to do today is start off by talking about how can we show that a limit does exist. So it's going to turn out that if we were to look at this example on the next page, example of taking a limit as xy approaches the origin of x to the fourth minus y to the fourth over x squared plus y squared, it's going to turn out that that limit does exist. But we have a problem. And I forget who mentioned this on Friday, but in Calc 1, you can typically show an overall limit exists by taking the limit from the left, the limit on the right, and show that they're equal to each other. You basically can just evaluate the limit as x approaches your point from all possible sides, from both of them, left and right, and show that those two one-sided limits come out to the same thing. Why are we going to have a much harder time doing that in this example? Where we take a limit as xy approaches 0, 0 of this expression. Why can't we just check the limit from each possible direction and show that it comes out to the same value? Okay, the problem is there's not just two directions we'd have to check this time, there's infinitely many. So we can't do the approach from Calc 1 where we just take the limit from each direction and show that they're equal, because that works when there's only two directions to check, but when there's infinitely many, we can't do it that way. So before we start evaluating this though, there is one other way that we could show that a limit does exist in Calc 1. And I want to talk a little bit about that first. Here's just a quick Calc 1 example of something that we should be able to take a limit of, show that this limit does exist, without actually having to check a left and right hand limit as x goes to 0. So how could we evaluate this limit without having to necessarily check each direction?
Cancel out x.
Thank goodness, I was worried you were going to tell me to use L'Hopital's rule again. Yeah, we could just cancel out a factor of x from the top and bottom, which is totally okay to do as long as x is not equal to 0. And in this case, since we only care about x values that are close to 0, it's totally legit to just cancel out x's from the top and bottom, which will give us the limit as x goes to 0 of just x squared by itself, or x squared over 1 if you wanted to write it out that way. And how would we take a limit as x goes to 0 of just plain old x squared?
You can just direct sub 0 in.
Yeah, at this point, no reason why we can't just plug 0 in for x. And if we do that, we'll end up with 0 as our answer. So in other words, we could evaluate this limit. We didn't have to do a left and right hand limit to show that the limit exists. We just showed that if you kind of cancel out the troublesome factor of x from the top and bottom, you end up with the equal limit of something that you could just directly plug x equals 0 into. And it's going to turn out to be the case that I think you can do something very similar here in this example, where we should be able to cancel out some pesky things in the top and bottom of this fraction, x to the fourth minus y to the fourth over x squared plus y squared, in a way that will allow us to kind of cancel things out and hopefully end up with something that we can just plug 0, 0 into. So let's take a look at this. Is there any way that we could factor the numerator? In other words, factor x to the fourth minus y to the fourth in a way that would give us a factor of x squared plus y squared that we could cancel out in the top and bottom. So in other words, how can we factor x to the fourth minus y to the fourth in a way that will give us a factor of x squared plus y squared? Oh no, reverse spoiling. What?
Well, it's factor between x squared plus y squared and x squared minus y squared.
Let's see. We multiply. If we were to FOIL this out, we get x squared times x squared is x to the fourth. We'd get a plus x squared y squared from the inside terms. We'd get a minus x squared y squared from the outside terms. So those cancel out. And finally, we get a plus y squared times negative y squared is negative y to the fourth. Yeah, I think that checks out. And by the way, the way you can get that is using a kind of a difference of squares formula, using the fact that a squared minus b squared is always a plus b times a minus b. Same thing here, you just have to replace a and b with x squared and y squared respectively. And so now we can rewrite our original limit as just being the limit as xy goes to the origin of x squared plus y squared times x squared minus y squared all over x squared plus y squared. And now if we wanted to use a similar approach to what we did in sort of this Calc 1 example, what's something we could do to this expression that would allow us to evaluate this limit a little easier? Oop.
Cancel out the x squared plus y squared from the numerator and the denominator.
Bingo. Yeah. As long as x, y are not both 0, if x, y is any point other than the origin, x squared plus y squared is going to be something non-zero. It's going to be a positive number. And so, just like how we could cancel out a factor of x here in the top and bottom, because x was not, we didn't care about what happened at x equals 0, we could do the same thing here with x squared plus y squared in the top and bottom, because we, again, don't care what happens at the origin, only at points that are very close to it. Where x squared plus y squared would be something positive we're canceling out from the top and bottom, rather than 0. So we end up with a limit as xy approaches the origin of just plain old x squared minus y squared. And how would we evaluate that expression? That's a, sorry, I'm too enraptured with watching Tim come ever so closer to nodding off over there. Yeah, we could just plug in 0 to x and y. No reason why. This expression, we couldn't just plug in 0 for x and y because we get 0 over 0, which is bad. But here, if we just plugged in 0 for x and 0 for y, we'd end up with a single numbered answer of 0. So what we did was essentially the same thing as in this Calc 1 example. We couldn't evaluate our limit directly from the start by plugging in 0 for x and y. We also couldn't really try the approach where we check every direction because there's infinitely many we'd have to check. But by kind of canceling out a troublesome factor of x squared plus y squared from the top and bottom here, we were able to get something that we could just plug 0 into directly. Or 0 for x and 0 for y. By the way, if we were to try and take this limit from any single direction, as x, y approach the origin from along y equals x equals 0, y equals 0, y equals square root of x, any path approaching the origin that we tried to evaluate this limit along, it's always going to come out to 0. The fact that the limit without specifying a direction comes out to 0 means that if you were to approach the origin along any direction, you're always going to get 0 every time. Fortunately, we had this nice approach that didn't require us to actually pick a direction for showing that the limit does exist. Whereas if we wanted to show the limit did not exist, we would just have to find 2 directions along which we'd get different limits. Any questions or comments about what we did here? So next up, I want to give you all a couple minutes to try working on a couple limit examples yourself, specifically the ones on the next page of the packet. What I would like for you all to do is to, first of all, to evaluate a limit as x comma y approaches -2 comma 4 of the expression x plus 2 to the 4th over x plus 2 squared times y cubed. And also, the other one on this page that I'd like for you all to try out, I'd like for you all to take a limit as x comma y approaches 0, 0 of absolute value of x over the square root of x squared plus y squared. Go ahead, see if you can kind of use the techniques we've talked about to evaluate these 2 limits. And as always, you're welcome to talk to the people sitting around you or to flag me down if you feel like you have questions or you're stuck and not quite sure how to get started. Nope. You can do that. You can do that for products, but not for sums. So one thing to keep in mind is that the square root of x squared plus y squared is not the same thing as square root of x squared plus square root of y squared. So don't try and break it up like that. Good question. If you feel like you're not sure how to get started with either of these, as always, I encourage you to check with your fellow classmates to see what they did. Or if you want, you can find me out and I'll give you a hint as to approach you might take. And if you finish these two, there's a couple more problems on the page after this that I encourage you to take a look at. I'll say I did not use the conjugate, but that doesn't mean there isn't an approach that doesn't mean it could be helpful. Huh? Is there anything you can see? Is there any easy way you can see they cancel things out from the top and bottom?
Can you separate it into two different lines?
You can't touch them. Stay away. They burn you. You can't take derivatives, which is something we're going to be talking about later this week. I'll say this. If you can't find out a way to cancel things out and get something to plug in, maybe try an approach where you look along a few different directions to see what happens. This is true. Or zeros. Yeah, same suggestion. Maybe try looking at a few different directions and see if, like, along x equals 0 or y equals 0. Anything interesting. As always, I'm here. Close to it. It's actually the square root of the one we did before. It's not, I'll say this. In general, if it did exist, it wouldn't necessarily exist as this one.
So
You can't just square the top and bottom. Yes, these don't necessarily match because just squaring the top and bottom will give you a different number. If it's like 2 over 1, for instance, it becomes 4 over 1, which gives you something in general. In this case, that would just be easy. Alrighty, so let's come back together and talk about these for a couple minutes. Anyone like to share how they approach this first limit? As xy approach -2, 4 of the expression x plus 2 to the 4th over x plus 2 squared y cubed. I saw several of you had some good ideas on this one as I walked around the room. Tim?
Separate the top into x plus 2 squared times x plus 2 squared.
Okay, so rewrite this as just two different copies of x plus 2 squared. Sure.
So you can simplify or cross out an x plus 2 squared on both the top and bottom.
Ah, okay. So in other words, you just want to simplify. You just want to cancel out two factors of x plus 2 squared. Totally legit because we're looking at a limit here. So that would leave us with x plus 2 squared over y cubed. And can someone else take over from here? How would we be able to evaluate this limit as xy approaches -2, 4 of this expression? Oh, let's see. Who do I want to pick on then? Daniel, any ideas for this one?
I would just plug in x is -2 and y is 4.
Sounds good to me. At this point, just plug in our values for x and y. So if we do that, we'll get -2 plus 2 quantity squared over 4 cubed, which is going to give us 0 over 64. And in the end, we do get a limit here that this expression is going to come out to 0. So this one was like the one we just did, and that we could cancel out factors of things in the top and bottom. That'll leave us with an expression we can just plug in our x and y for. How about the second one? Limit as xy approaches the origin of the absolute value of x over square root of x squared plus y squared. This one is a little bit nastier in that there's nothing obvious you can really cancel out in the top and bottom here. There is no kind of single factor of, if you wanted to, you could rewrite absolute value of x as being square root of x squared. But, there's still not, you can't cancel out a factor of square root of x squared from the bottom because we're adding a y squared to it here.
I tried just doing it from different directions where it didn't seem an easy way to cancel it with both x and y, and so I tried where I just had y equals 0, and I approached it along the x-axis.
Okay, so I think that's a great approach to take. If you're not sure how to cancel things out, get it in a nice form where you can just plug in your numbers, maybe try looking along a few different directions, see if it becomes any easier or if you learn anything. Can you repeat? Can you remind me which direction you said you tried?
I came along the. I just had y equals 0 and x approach 0.
Okay, simple enough. So if we take the limit of this expression along x equals 0, what I think we're going to get is we'll end up with a limit as y goes to 0 of this, where we can plug in 0 for x. We'll get 0 over the square root of 0 squared plus y squared, which is the same as limit as y goes to 0 of 0 over square root of y squared. And what is that going to come out to? We're going to try and take a limit as y goes to 0 of plain old 0 over square root of y squared. There? Why is that?
Because if you divide by smaller and smaller numbers, the numbers you're going to get are going to get bigger and bigger.
This is true. However, we also have a 0 in the... If we had like 1 over something going to 0, then I think you would be absolutely right. 0 over something going to 0, a little bit different, because we have some sort of unstoppable force immovable object scenario where 0 over anything is going to be 0, but anything over something going to 0 is usually going to infinity. So how can we reconcile this for this particular limit?
No matter what you told me for y.
I think so. In this case, since the numerator is exactly 0, while the denominator is just something that's getting close to 0, even if we were to plug in some very small value of y, like y equals 0.01, we'd end up with 0 divided by very small number, which is still just going to be 0. And so I think this limit's going to come out to 0 regardless. So you're right, Sarah, that if the numerator had been any constant other than 0 here, you're right that this expression would have gone to plus or minus infinity. I guess in this case, infinity, since it's always positive. Cool. So we know that if we take a limit along x equals 0, this expression is going to come out to 0. Are there any other directions we could try evaluating this limit along? Ellen? Along y equals x? Makes sense. Makes sense to try. So if we do that, we could take a limit as xy approaches the origin along y equals x of absolute value of x over square root of x squared plus y squared, which I think will give us a limit as x goes to 0 of absolute value of x over square root of x squared plus x squared, which would be a limit as x goes to 0 of absolute value of x over the square root of 2x squared. We just, on y equals x, we can just replace our y's with x's, or vice versa if you wanted to. EGAT. How do we evaluate this limit? Well,
Separate the roots. So square root of 2 times square root of x squared of x squared is the absolute value of x. So it's 1 over root 2.
I like it. So first of all, while we can't separate sum like this inside of square roots, we can't split this up into square root of x squared plus square root of y squared, we can separate products inside of square roots, meaning square root of something like x squared times y squared will be equal to square root of x squared times square root of y squared. So it's totally okay here to split up square root of 2x squared into square root of 2 times square root of x squared. And then Will made an interesting observation, which is that absolute value of x and square root of x squared are always going to give you the same thing. The reason being, square root of x squared will give you back just x if x is positive. Because you square it, you take the square root, they cancel each other out. If x is negative, then the square root of x squared will give you back the positive version of your x. And that's exactly what the absolute value function does. It gives you back the same number if it's positive, the positive version if it was negative. And then from here, you could do the old swoosh swoosh on it and end up with 1 over the square root of 2. So along the line x equals 0, we got a limit of 0. Along y equals x, we got a limit of 1 over root 2. What does that tell us about the overall limit?
It doesn't exist.
Overall limit does not exist. Because it's not the same along all directions. Turns out this one, there is no nice way to kind of cancel things out into something you could plug numbers into. If depending on the way in which you approach the origin, you will get a different value along different paths. So if I were to ask you a question on a quiz, evaluate some limit, it would be up to you to kind of determine, do you think this is one where the limit does or does not exist? And if it does exist, and so that you can kind of cancel things out in a nice way to eventually get to some point where you could just plug the numbers in. And if you think that the limit does not exist, if there is no way to cancel things out nicely, then you just have to find two separate paths approaching your A comma B, along which the limits go to different values. So in this case, the limit didn't exist, and we found two different paths approaching the origin, along which we could find different limits. Whereas over here, the limit did exist, and we were able to kind of cancel out some factors of x plus 2 from the top and bottom to get us to a point where we could just plug in numbers. Anybody have any questions or comments on this limit finding process here? So next up, I want to spend the rest of today's class talking about what it means for a function to be continuous, specifically for multivariable functions. So, just as a little bit of quick review about continuity from Calc 1. Let's say we were looking at a function f of x that does something like this. And if this is our function f of x, the question I have is f of x continuous at x equals a here? Just from eyeballing the graph, what does your gut instinct tell you about whether or not this function is continuous at the value of a that I Alan?
Yes.
Why is that?
The circle's filled.
Let's say that.
Closed circle.
Ah, there's a closed circle there. What about this one? Would you still say that's continuous? Why not?
It's an open circle.
Ah, but there's a closed circle here.
It's not on the limit.
It's not on the limit. Ooh, what does that mean?
Like it's not.
So in other words, the actual value of the function there is not the same as the limit?
Yeah.
Yeah, I would agree. And going back to the original graph for a second, sorry to keep changing it up on you all. I would say that f of x is continuous here at x equals a, and the reason is because, yes, the reason is because if you were to take a limit as x approaches a of our function, you actually get the same thing as f of a. Meaning the value of the function at x equals a, in other words, y equals L, is going to be the same as the limit as x approaches a. Intuitively, it means you could find the limit of this function at a by just plugging a into the function itself. So, whereas with something like this, this is g of x, and this is our a, I would say g of x is not continuous at x equals a, since what is true for this particular function? What about this g of x makes it not continuous at x equals a from looking at the graph? Someone other than Tim on this one. This is when we get more people in the class involved. What about this function makes it not fail to be continuous at x equals a? No?
The limit does not equal f of a.
Yeah. Since whatever the limit is, that would be this y value, say L, limit as x approaches a of g of x is not equal to g of a. So this would be g of a here, this y value, but the limit is something up here. Would the function be continuous if there is no g of a? Emily? You reject your answer?
I still think it's no, because a g of a is just undefined, and that doesn't equal what it's going to be approaching.
Yeah, I would say in this case, g of a just doesn't exist, so it can't possibly be equal to the value of the limit here. So this would be another is not continuous. How about that one? Emily, want to try again? Yeah, there's a jump discontinuity here today, and so I would agree that would be another way that the limit could fail to exist, or the function could fail to be continuous. So in order to have continuity, you need that both of these things exist, both the limit exists and f of a exists, and they had to be equal to each other.
What if a were open circle, like where g of a is?
Like this?
Yeah.
Y'all think, is that continuous today? I think this one would actually fail both conditions. Both the limit would not exist and g of a would not exist. And so we have two different reasons why this function would fail to be continuous today.
So they can't both equal do not yet exist.
They can both not exist, and that this is not a double negative becomes a positive situation where if two things fail, it suddenly works. In this case, I would say we have two different reasons to say why g of x fails to be continuous here. In this case, because the limit does not exist, and because g of a does not exist. So in order to be continuous, you have to have all three. The limit has to exist, the value of the function at your point has to exist, and they have to be equal to each other. So it's going to turn out to be the case for multivariable functions that the same sort of thing has to occur in order to have a continuous function. In general, we can say that a function f going from some Rn to some Rm is going to be said to be continuous at a at a vector x equals a if the same three things end up happening. First of all, if the limit as x approaches a of our function exists, meaning the limit as x gets really close to vector x gets really close to vector a has to exist. Second, you need that f of a exists. And third, they have to be equal. That the limit as x approaches a of your function f of x has to be equal to f of a itself. And we'll do an example here in a second where we look at that sort of thing happening or not happening. So if you get all three, then your function is going to be continuous at x equals a. If any one of these fails, or yes, Jacob, if multiple of these fail, then the function is not going to be continuous. It's going to be discontinuous at a. We can also say in general that f is just a continuous function without specifying the a if f is continuous at all values a in the domain of the function. So in other words, if we could say that a function f is just going to be a continuous function as a whole if whenever f of a is defined, whenever f of a exists, the limit as x approaches a of f of x also exists. and is going to be equal to f of plain old A. So if it's the case that for every value of A in your domain, meaning anytime f of A exists, that the limit is going to both exist and be equal to the value of the function, we're going to say that our multivariable function is continuous. And if there's any value of A in the domain of your function where this doesn't happen, where the limit doesn't exist, or if the limit is something other than the value of the function, then your function is not going to be a continuous function. So let's look at a couple examples where we just kind of take a look at two different examples of multivariable functions. And for each of these functions, I'd like to determine whether or not they're continuous or not. So to start off, let's look at an example where we're going to take f of x comma y comma z is going to be equal to x plus y plus z, comma, xyz plus 2, comma, sine of x minus cosine of y plus tangent of z. So we have a function here, in other words, that goes from R3 to R3. Our inputs are three-dimensional vectors, because you have an x, y, and z input, and our outputs are also going to be vectors in R3. The codomain is R3, since our outputs have 3 dimensions to them as well. And I'd like to determine whether or not this function f is continuous or not. That's a complicated function. So I propose, instead of trying to look at the function f as a whole, let's just look at the component functions of f to start with. So if we were to break f up into 3 separate component functions, f1, f2, f3, what would our first component function be for this function f? In other words, what would our f1 of x, y, z be equal to? Whoop.
X plus y plus z.
Yeah, x plus y plus z, just the first component of our output vectors. How about our second component function? No?
XYZ plus 2.
xyz plus 2. And finally, our last component function. Who did I heard from? Laurie, how about our F3 here? Yeah, sine x minus cosine of y plus tangent of z. So we have our 3 component functions. So let's see if we can determine whether or not each one of these 3 functions is continuous. So how about f1 to start? So f1 takes in 3 variables, an x, a y, and a z, and just spits out the sum of all 3 of those input coordinates. f1 of x, y, z is x plus y plus z. So what do y'all think? Is that going to be a continuous function? Or is there going to be some vector in the domain, in other words, some vector x comma y comma z, that the limit of this function at that vector is not equal to the value of the function itself, x plus y plus z? Who am I? How about last year? Do you think that f1 here is going to be continuous?
Yes.
Why?
Just putting in a limit, I can't find any areas where f of a wouldn't exist.
Yeah, it's certainly defined everywhere. The domain is all of R3. Is there anywhere where the limit, though, is going to be different than the value of the function? I agree. I think f1 here is going to be continuous because anywhere that the function is defined, meaning anywhere in R3, you can always evaluate the limit at any point in R3 by just plugging in those numbers for x, y, and z into the function. The limit of this expression is always going to be equal to the actual value. How about f2? We're taking in 3 coordinates, multiplying them all together, and then adding 2 to whatever that gives us. Is that going to be continuous everywhere? Wait.
Yeah, it should be.
I think so too. We're never going to have any issues with just multiplying x, y, and z together and adding 2 to that. If we wanted to take a limit as x, y, z approach, I don't know, 1, 3, 5 of this expression, we could find that limit by just plugging in 1, 3, and 5 for x, y, and z respectively. Finally, how about this last one? f3 of x, y, z equals sine of x minus cosine of y plus tangent of z. That's
Not continuous, tangent z is going to be problematic.
how so?
Because the function is undefined, I believe it's when z is equal to multiples of pi.
Yeah, tangent's going to be undefined at odd multiples, specifically of pi over 2. That being said, does that actually cause us any issues? In order for our function to fail, in order for our function to be a continuous function, it needs to be the case that for any value of any vector A in the domain, meaning if we only care about input vectors that give us an answer that's defined, so I think we would be excluding those vectors that you looked at, that you mentioned, Sarah, the things where z is a pi over 2 multiple. Any vector where f3 is defined, I actually think the limit is going to be equal to the actual value of the function. And so I'm actually going to say f3 is continuous even though it's not defined at any vector x, y, z, any vector x, y, z where z is an odd multiple of pi over 2. In other words, points where cosine is 0. And in this case, the reason why I would say f3 is continuous, I would say f3 is continuous since at any x, y, z in the domain of f3, meaning at any vector x, y, z where z is not an odd multiple of pi over 2, it's going to be the case that the limit as x, y, z approaches, instead of saying x, y, z, let's say a, b, c. At any time x, y, z approaches a, b, c of f3 of x, y, z, it's just going to be equal to f3 of a, b, c. Meaning, if you wanted to take the limit of this function as x, y, z approach something like 0, 2, pi over 6, you could just plug in 0 in for x, 2 in for y, pi over 6 in for z, and that would tell you what the value of the limit is by just plugging it into the function. Hmm?
So why is this different than when like when we have a
Hole in our graph?
discontinuity? Yes.
Yeah, it's a good question. So let's take a look at this function really quick. Let's say this is our f of x. Is this a continuous function? Why? Let me wiggle my point. Why is that not a continuous function?
Because the limit as x approaches a does not equal f of
So the function's not continuous at a, in other words.
a. Right. So
Does that matter?
yes. Wait, so it is continuous or?
It actually is a continuous function. The reason being, for any value of a in the domain of this function, the function is continuous. There's only one value of x where this function is not continuous, and that's at a value of x outside the domain of the function, because there is no filled-in point at a here.
I got you.
So this is a continuous function. Since it's continuous anywhere it's defined. If I were to put in like a point up here, actually try and fill in a point at x equals a up here, this would no longer be a continuous function because now a is in the domain of the function and your function is not continuous there. But if your function fails to be continuous at a point outside the domain of your function, it's still okay. Your function can still be considered to be a continuous function.
So you only have a discontinuous function if you have either an infinite discontinuity or a jump discontinuity with one side filled in?
Not necessarily, because this wouldn't be either of those. It's not a jump discontinuity, and it's not infinite. This would just be a point discontinuity, but it would still be a non-continuous function because there is a value in the domain of your function. Since there's a filled-in circle, a is in the domain where the function fails to be continuous. The problem is you can't say that your function is discontinuous by looking at some value where your function's not even defined. If that makes sense.
So if you had a jump discontinuity with neither side filled in, would that?
Like this?
Yeah.
This would be a continuous function. This would not. Ditto with infinite discontinuity. Y equals 1 over x is a continuous function. Any other questions or comments about why f3 here is continuous? It's a very subtle reason. The fact that for your function to fail to be continuous, you need to find some value in the domain of your function at which it's not continuous. If it's not continuous at some point outside the domain, then who cares? That doesn't affect whether or not your function is a continuous function as a whole. So let's go back to this example, this big F that we were just looking at. Our F1, F2, and F3 are all continuous. It's going to turn out to be the case that that means that F is continuous. Since all its component functions are continuous, F as a whole is a continuous function. And in general, that's the way that you would check if a function with multiple component functions to it, like this, is continuous or not. You just check the component functions. If the component functions are continuous, then the function as a whole is continuous. If any one of these three component functions had failed to be continuous, then the function as a whole is also not a continuous function. So you have to kind of keep in mind that breaking up a function into its component functions can be used to help you determine continuity or something like this, where the output vectors are not just scalars, but have multiple components within the outputs. Let's look at one more example here. Last example I want to look at today is a g of xy here. want to determine, is the function g of xy given by x squared minus y squared over x squared plus y squared if xy is anything other than the 0 vector, and 0 if xy is the 0 vector. I want to determine whether or not this piecewise function is continuous. So something to keep in mind is if xy is equal to 0, 0 means for anything other than the origin specifically, we wanted to plug in something like g of 0, 3, we would use the top part of the function. We'd get 0 squared minus 3 squared over 0 squared plus 3 squared. The only time you use the bottom half of the piecewise function is if your input is specifically 0, 0. We have to define it differently at the origin because it, this top expression is undefined at 0, 0 itself. So here's my question. Is this a continuous function? Or is there some point in its domain, in this case the domain is all of R2, where the function fails to be continuous? So right off the bat, does anybody have, is this function ever going to fail to be continuous anywhere other than at the origin? Tim? I agree. I think x squared minus y squared over x squared plus y squared is going to be continuous everywhere it's defined. So let's write that in. Note that x squared minus y squared over x squared plus y squared is continuous everywhere it's defined. Which means, since at all points except for one point, g of xy is defined by this function, that's going to tell us that g of xy is automatically continuous everywhere except potentially one point. What one point do we still need to check whether or not our g of xy is continuous at? If the x squared minus y squared over x squared plus y squared piece is continuous everywhere over this top section of the domain, what one point do we still need to check whether or not our function is continuous?
The domain.
The domain? The domain is everything, all of R2.
But we don't know if it's continuous with the function. Because we have to check the limit approaching the domain equals.
You mean the origin?
Yeah, the origin.
Okay, yeah. Gotcha. I was gonna say I'm not sure what you mean by saying is it continuous over the domain. It's like, yeah, that's what we're checking as a whole. So the one point where we still need to check is gonna be at 0, 0.
Yeah.
Because it's possible that even though this top part of the function is continuous everywhere other than the origin, it's possible that at 0, 0 itself, this function still fails to be continuous. What would need to happen at the origin if this function was continuous there? So in other words, how could we check whether or not g of xy is continuous or not at the origin? Yeah, it would have to be the case that we could say that g of xy is continuous at the origin if the limit as xy approaches the origin of g of xy would have to be equal to g of 0, 0, which based on how we define that is 0. If the limit of this function as xy approaches 0 is anything other than 0 or is undefined, then the function's not going to be continuous at the origin. But if this top function, but if g of xy does come out to a limit of 0 at the origin, then g of xy is going to be continuous at the origin, and g of xy is therefore continuous everywhere on its domain. It's a continuous function. So let's check that out. Unfortunately, we can't just plug 0, 0 in very easily and to check to find out what the limit is here. So what could we do if we wanted to determine what this limit is? Oop.
Just run along a certain axis, just say y is equal to 0, and x is equal to 0, just to check and start checking to make sure that it works for all directions.
Okay. So one way we could show that this limit does not come out to 0 is to pick a single direction and show that it doesn't go to 0 along that one direction. So since you suggested the idea, which direction would you like to check?
Let's do where y equals 0.
Y equals 0? All right. So if we were to take a limit as xy goes to 0, 0 along y equals 0, since we're looking as xy is only getting close to the origin rather than at the origin itself, we're going to use the top half of the function, g of xy. So that's going to be the same as the limit as xy approaches 0, 0 along y equals 0 of x squared minus y squared over x squared plus y squared. Again, we're using this top piece because we're only looking at points close to 0, 0. And close to 0, 0, g of xy behaves like this top half of the piecewise function. So along y equals 0, we're going to get a limit as just x goes to 0 of x squared minus 0 squared over x squared plus 0 squared, which is going to be a limit as x goes to 0 of x squared over x squared. And what's the limit as x goes to 0 of x squared over x squared going to be? Oh.
1.
Yeah, so we can cancel out x squared from top and bottom here. So in other words, along the x-axis, along the line y equals 0, meaning as xy approaches 0, 0 from the left and from the right, we know that our limit of the function g of xy is going to 1. What does that tell us about continuity?
Function is not continuous at 0 because it would have to be going, the limit would have to be going to 0.
Yeah. So this right here tells us, thus, we know that the limit as xy approaches 0, 0 of this function, without specifying a direction, we know that that limit can't possibly be equal to 0. Can't possibly be equal to g of 0, 0. Why? Because we found a single direction along which the limit came out to 1. So that means that the limit as a whole either has to be 1, or it's possible that the limit does not exist. We'd have to check other directions to determine does the limit exist or is the limit just does not exist because it's different. But either way, since it's not 0 along every single direction, that tells us whatever the limit is, it's either 1 that does not exist, doesn't matter which in this case because it can't possibly be 0, which then is going to tell us g of xy is not continuous at the origin at 0, 0, which means g of xy is not a continuous function. Because 0, 0 is a point in the domain, We know it's in the domain because it's said to be 0 at 0, 0. But it's a point in the domain where the limit of the function can't possibly be equal to the value of the function. The limit as xy approaches the origin of our function can't possibly equal g of 0, 0 itself. That means our function fails to be continuous at the origin and is not a continuous function. Right, it's going to wrap it up for continuity. There's a few theorems in this packet regarding properties of limits and continuous functions. I'm not going to write them out on the board because it's the same limits as in Calc 1. Things like the sum of continuous functions is continuous and so forth. When we come back on Wednesday, we'll start with a quiz over limits and continuity and then move on to talking about derivatives. Have a good day, everybody.